in some sense, these questions are really good in that if you can do these questions and you can do them with confidence, you can do what's on the exam. I'm not trying to encourage you to only do these questions. So you'll see there's two pieces of advice. And the first piece of advice is to do hard problems. The way you get better at math is you do math. You have to practice. And you have to do hard problems. Now, when I say hard, I don't mean look for the one that has crazy arithmetic or weird algebra, because that's not what we really want to be testing you on. By this point, we assume you're getting okay with your arithmetic and algebra. And if not, Calc 2. Wow, that's like really good at getting your arithmetic and algebra skills finally sharpened. So when we say hard problems, we mean hard in that you have to think about them. So we really hope that one of the things you get out of taking a calculus class is that you've learned to think. And that's our measure of success in some ways. How well have we gotten people to think? And the more that we can get you to think, the better. Now, the second piece of advice is take care of your health. So get plenty of rest. We have people sometimes who will do all-night study sessions for 2 or 3 days before the exam, show up at the exam, and they fall asleep. It's a bold move. Doesn't usually work out. It's better to get plenty of sleep. And also, get up, do a little bit of exercise, go for a short walk, eat good food. When your body is healthy, you're able to think better and you're less likely to make mistakes. That's the basic idea. All right, well, with that out of the way, we're ready to begin. So we're just going to go through and just problem after problem after problem. Now, I'm going to do my best not to make mistakes. If I make mistakes, just go ahead and say, whoa, you should have put it like a 7 there. And no, it'll be okay, we'll fix that. But the ideas are there. And those are the important things. So we're going to start with some true-false. Determine if the following statements are true or false. No justification is required. In other words, we're just true or false. We don't have to explain why it's true or false, which is good. A continuous function is always differentiable. Well, true or false? Now, this is kind of tricky, right? Because we know a lot about continuous functions. Continuous functions are the kind where you don't have to lift your pencil. And the differentiable means that you can take derivatives. And they seem to be closely connected. So here, we have to think about what's being said. So if we have a continuous function, it's always differentiable. So we start thinking about, are there examples that we saw in the class where something was continuous but not differentiable? And so in other words, didn't have a derivative. Well, there was a simple example, which is the absolute value. If you look at absolute value, that's nice and continuous, but at that point at the bottom where two sides come together and they make the v, it's not flat. And so it's not differentiable. Okay, so it's continuous, but it's not differentiable. So this is an example where the statement doesn't hold. And so if once it doesn't hold, in one case, we say, look, it's not a true statement in general. So that's a false statement. Now, there are plenty of continuous functions which are differentiable, but even just one makes it a false statement. Okay, so A, false. All right. Well, okay, B. For any continuous function, f of x and g of x, we have that if we want to take the derivative of the product of f times g, it's f prime of x times g prime of x. It's kind of like a product rule. Now, this doesn't quite feel right, because I seem to recall that if I want to take the derivative of f times g, there's a product rule for that, which says what you do is it's f prime of x times g of x plus f of x g prime of x, which doesn't match with what they have written here. And so that doesn't seem right. Okay, so we're suspicious. We're suspicious. Now, to convince ourselves, we should just do a simple example. Let's do a simple example just to make sure we're not crazy. Suppose I say f of x is x and g of x is x. Well, if I look at the side that says take the derivative of x squared. Oh, that's 2x. On the other hand, the other side says take the derivative of x times it by the derivative of x. So what looks like 1s, those are actually primes. Well, that's 1 times 1. Yep, 2x is not 1. Those aren't the same. So this is false. Okay, so part B, that's a false statement again. Woo, boy, 2 for 2. All right. Okay, well, let's see part C. For f of x equals x squared and g of x equals x minus 2 to the negative 2, we have that the derivative of f times g is f prime times g prime. Oh, wait a second, we just did that. That was part B. Shouldn't that one be false? Well, this makes us suspicious. Now, let's check. Before we jump into saying false, let's actually just do the computation. So we take x squared times x minus 2 to negative 2. We're going to take the derivative of that. That's what the prime means. All right, so taking the derivative, well, product rule, derivative of the first times the second plus the first times the derivative of the second. And then we use the chain rule. Negative 2, x minus 2 to negative 3 times the root of the inside, which is 1. All right. Well, we can clean that up a little bit. They both have x minus 2's in them, and so we can pull that out. So if we pull out x minus 2, you should pull out the smallest power, which is negative 3, because between negative 2 and negative 3 is certainly smaller than negative 2. So if we pull that out, let's see, we can also pull out a 2 and an x. All right, so 2 and an x, what's left? Well, we got the 2, we got the x. X minus 2 to the minus 2. Well, to get here, we had minus 3, which means I had to need an x minus 2 to the 1. That will make sure I end up with the right power. Here, I didn't get the minus sign, and I only got one of the x's. So minus x. Everything else I got. So if we clean this up, x and minus x cancel. Boom, boom. So this becomes minus 4x, x minus 2 to negative 3. On the other hand, the derivative of x squared times the derivative of x minus 2 to the negative 2, well, the derivative of x squared is 2x. Derivative of x minus 2 to the negative 2, minus 2 comes down, x minus 2 to the negative 3 times the inside, derivative of the inside, which is 1, which becomes minus 4x, minus 2 times 2x, times x minus 2 to negative 3. And lo and behold, they're the same. Whoa. So what does that mean? Well, it means that this is a true statement. Okay, so you got to be careful, because there are some things which are true in special cases, but not true in general. In fact, when it comes to teaching calculus, this is one of our biggest obstacles, where there's a couple times when something that would be nice to be true is true, for instance in this case, but in general it's false. But people get convinced, no, it worked for a special case, so it must be true in general. No, you got to be careful. You got to be careful. So this is false, false, true. Now, you might say, you know what, I'll just play the odds. I'll circle all false, or I'll circle all true. And we've gone to the point where it's like, we know students will do that. And in the recent past, such as in Calc 2, this last exam, we actually said, we know they're going to guess that way, so we're not going to make that happen, where we had all of the answers where nothing happened for one of the possibilities. We have a lot of fun writing these tests. So think about it. All right. Well, that was the true-false. Now we get to do the real fun stuff. Computation, calculus. Now, here we go. Find y of x, given that y prime is 2y squared e to the 2x. Now, what kind of problem is this? Well, what we have here is this is a derivative, and then there's the original function. So what this is a differential equation, because it's an equation that involves the derivative and the original function. So in particular, the only kind of differential equations we can do are what are called separable differential equations. Now, don't worry. Keep taking math. You'll get to learn how to do other differential equations as well. But how do you do these? Well, Simple process. Step 1, you separate. Step 2, you integrate. And step 3 is you uncomplicate. Now, you probably think, that doesn't sound like a real word, uncomplicate. You're right. But it sounds cool to have things that rhyme. So I'm going with it. Now, what do we mean by separate? Y prime is dy over dx. And what we're going to think of is we're going to say, well, let's really think of this as dy is one piece and dx is another piece. So we're going to put everything with the y on one side. So I'm going to leave the dy here, bring the y squared across. And then we're going to have everything with x on the other side. So 2e to the 2x dx. So everything with y on one side, everything with x on the other side. Now you might have to do a little bit of manipulation to get to that stage, but that's the idea. That's where you want to get to. So that's the separate. Now, the integrate. You integrate both sides. So here, well, how do you integrate y squared downstairs? I think that's y to the negative 2. And now, y to the negative 2, the integral of that is negative 1 over y. On the other side, you have e to the 2x times the 2. Well, that's not so bad. In fact, that should be something we can recognize. That's e to the 2x. Now, of course, that's the integral of the two sides. But don't forget that it's not just the integrate, but you always remember it's up to a constant. So don't forget your plus c. If you get your plus c, you're going to lose points because that's important. Because there's something we haven't talked about yet. We haven't talked about this part, the initial condition. We need that. So we're told that y of 0 is 1. So that means if we plug in 0, so when we say y of 0, this says when x is 0, y is 1. That's how you read the statement. So we read the statement. So we plug in 1 for y, negative 1 over 1, is e to the 2 times 0 plus c. Well, e to the 0 is 1. So we can move this across and we can conclude that c is negative 2. So updating, we have negative 1 over y is e to the 2x minus 2. And what do we want? Well, it told us to find y of x. So we want to get y by itself, which is pretty close. We're almost there. The only thing is that we have negative and we have the 1 over y. Well, we fix both. To fix the negative, multiply everything by a minus. That fixes the signs. And finally, to get the y, flip everything. So y is equal to 1 over 2 minus e to the 2x. And that's it. We're done. So, whoops, I forgot to check. Yep, check, check, check. All right. So we integrate, uncomplicate, really says solve for c, and then if you need to, solve for your variable. You don't always solve for your variable. There are cases when you say, well, I'll just rearrange things and see what I need. Given that f of negative 2 is 3, and f of 7 is 11, and that the average rate of change of f of x from x equals negative 2 to x equals 2 is thrice the average rate of change of f of x from x equals 2 to x equals 7, then determine f of 2. So, all right, this is interesting. Now, one of the things we have to learn is to recognize what kind of problem we're working with. There's a key word here, average rate of change. Now, when you see that key word, then you say, I think this is an average rate of change problem. Okay, yes. Well, that's kind of, some of them are more obvious than others. Okay, so what do we mean by average rate of change? So the average rate of change from A to B, that's f of B minus f of A divided by B minus A. So this is our key equation. This is what we need to know. Everything is going to go off of that fact. So we're going to read what we have here. The average rate of change from negative 2 to 2. So that would be f of 2 minus f of negative 2 divided by 2 minus negative 2. So this is, again, the average rate of change from negative 2 to 2. Is thrice, so is another way of saying equals. Thrice is just a fancy way of multiply by 3. The average rate of change from 2 to 7. So f of 7 minus f of 2 divided by 7 minus 2. So we take the average rate of change formula plus the statement that was given to us, and it produces this equation. Now we update with what we know. We know f of negative 2 is 3, and f of 7 is 11. So we get f of 2 minus 3 over 4 is equal to 3 times 11 minus f of 2 over 5. Well, there's only one thing we don't know, which is f of 2, but we have one equation. And so now we cross multiply, get rid of fractions. I don't like fractions. Fractions challenge me. So 5f of 2 minus 15 is equal to 12 times 11 minus f of 2. Well, 12 times 11, that's 132, and then minus 12 f of 2. So we'll move things across, or at least move them around. We can conclude that 17 times f of 2 is equal to 147. So I just add the 15, get 147. And so at the end, f of 2 is 147 divided by 17. All right, exactly like you would have guessed. No, you wouldn't have guessed that. You do the work. You do the work. No guessing required. All right. Can I put something back up? Yes? There seems to be a query. Am I going to be posting this? Absolutely. In about 4 hours from now, you'll have a link. And all the notes will be scanned, and you can listen to this again, and even including this very part right here about how you can listen to it again. So yes, this will all be posted. So determine the horizontal asymptotes of f of x, which is 5 e to the x minus 2 arctangent of x over e to the x plus 1. Justify with limits. Now, of course, how many horizontal asymptotes can we have? Now, asymptote says what happens as you go off to something. In particular, there's this notion of something's going off to infinity. Now, there's two kinds. There's horizontal and vertical. The horizontal says we're going, the inputs are heading off towards infinity. Now, vertical is a different kind. How do you recognize vertical? Well, vertical says the output's going towards infinity, and usually you look for divide by 0. That's usually a sign that there might be a vertical asymptote. Not guaranteed, you have to check, but that's where you look for. Why do I say not guaranteed? Sine x over x. That doesn't go to a vertical asymptote, but the denominator goes to 0. All right, sorry, I'm getting sidetracked. Back to our regularly scheduled problem. Horizontal asymptotes. So when we're talking about horizontal asymptotes, we want to ask what happens as we get large. So, in particular, what happens as we head to infinity? So we look at the limit as x goes to infinity of f of x. Well, that's the limit as x tends to infinity of 5 e to the x minus 2 arctangent of x divided by e to the x plus 1. And if we look at this, well, there's a couple of things. The 1 certainly isn't changing much. Arctangent of x, that's a nice function. You might know. It looks like a tangent piece turned on its side. So it actually does approach asymptotes at pi over 2 and negative pi over 2. And so since we're heading towards infinity, that's approaching pi over 2. All right. But then the e to the x. Well, e to the x is getting big. And so as we head off to infinity, we have huge stuff upstairs, huge stuff downstairs, which means it's right now it's tending to infinity over infinity. All right. Well, that's no good. That doesn't tell us anything. Well, it does tell us something. It tells us more work is required to get the answer. So how do we do this? Well, you can try the L'Hopital, but oftentimes that's not the only thing you have to do. In fact, sometimes the L'Hopital won't work. Here's a better idea. Let's think about what's getting big. Now, in our case, the answer is the e to the x is getting big. So what you can do is you can pump the brakes. Now, that's the idea is we're going to try to slow things down in a controlled manner. So we're going to say, aha, it's the e to the x that makes everything big. So multiply top and bottom by that thing that's getting huge. So that's going to help us slow down at just the right speed. So why do I say just the right speed? I don't want to go to infinity, and I don't want to go to 0. That's the right speed. So 2 arctangent of x over e to the x upstairs, 1 plus 1 over e to the x downstairs. And now as you go to infinity, you say, aha, 5 and 1 are great. Here you get 1 over a big number. Here you get something over a big number. And so this is going to be 5 over 1, because that part goes to 0, and that part goes to 0. So 5. All right, so the answer is 5. And it's a horizontal asymptote, so it's a y equals. Okay, are we done? Well, that's a rather dramatic question. You should be suspicious. No, we have white space left on the page. We need more things to do. Well, because we said, what happens as you go that way? There's also this way. So we're going to go that way. Negative infinity. Now you might say, do we have to check both? And the answer is yes, you have to check both. Because a couple things can happen. It's possible that you have an asymptote on one side, but not the other side. And it's also possible they have asymptotes on both sides, and they're different. So you have to check. So 5e to the x minus 2 arctangent of x over e to the x plus 1. Now again, before we do anything, let's just check what happens. Now previously, e to the x was getting huge, but that's because we were going to positive infinity. Now we're going to negative infinity. E to the x goes very small. So that's going to go to 0. Similarly, 5e to the x is going to get very small. That's going to go to 0. 1 is going to be 1. And arctangent of x, well, we follow that, and that's going to approach negative pi halves. So we see it's going to be 0 minus 2 times pi halves over 0 plus 1. I don't need to do anything fancy. There's no 0 over 0. There's no infinity over infinity. So it's just what it is. And, whoops, I put pi halves. There should be negative pi halves, and minus 2, which means that our answer is pi. Okay, so that's that one. So if we have 5 and pi. So here, there are 2 horizontal asymptotes, and they're different. So there they are, y equals 5 and y equals pi. And we have limits to justify. All right. Well, let's do another limit problem. Find the limit as x goes to 0 of 1 over x cubed integral 0 to x of sine of t squared dt. Now, this is kind of a strange looking limit here, but another way to write this is 0 to x, forget the limit, sine of t squared dt over x cubed. So really emphasize that it's something over something. Now when we see this, what's happening? X is going to 0. So x is going to 0. That means downstairs, the x cubed, well, that's going to go to 0. Now upstairs, well, 0 shows up in the bounds. So we're going 0 to 0. So we're going integral 0 to 0 of sine of t squared dt. But the bounds match. If the bounds match, that means you get an answer of 0. So this is 0 over 0. All right. When you see 0 over 0, what does that indicate? L'Hopital, and really it means more work is coming. Now, of course, we've got the fraction already. We're in great form for L'Hopital. So we're going to apply L'Hopital. Oh, L'Hopital, mon ami. Okay, it's a great day whenever you get to apply L'Hopital. All right. Now remember, this isn't a quotient rule. It's you take the derivative of the top and the derivative of the bottom. Now the downstairs is pretty straightforward. Derivative of x cubed, 3x squared. The upstairs, you got to think a little bit. So what do we have? Well, we're trying to take the derivative with respect to x of the integral from 0 to x of sine t squared dt. And you might remember that there's something called the Fundamental Theorem of Calculus. And this is a very fun theorem. You see, it even starts, Fundamental Theorem. And it says if you're taking the derivative with respect to x, integral from any constant up to x of f of t dt, that's just f of x. So it really says, look, it's easy to take derivatives of functions. You just get what you started with. So in our case, the derivative from integral 0 to x of sine of t squared would be sine of x squared. So that's what goes upstairs. All right, now we see what happens as we go to 0. Well, this is going to go to sine of 0 over 3 times 0, which is 0 over 0. So what do we do? Do it again. Limit. X goes to 0. Okay. Downstairs, that's easy. 6x. Upstairs, use chain rule. Derivative of sine is cosine times x squared times the derivative of the inside, which is 2x. Okay, so this goes to cosine of 0 times 0 over 6 times 0, which is 0 over 0. So what do? Whoa! Again! Oh, l'hôpital, mon ami! You are such a good friend. Downstairs you get 6. Now, good news. Game over, man. Game over. Whatever happens has to happen now, because that 6 can't go to 0. It's going to go to 6. All right. So what does happen? We've got to do the upstairs too. So take the derivative. Derivative of cosine, negative sine of x squared times 2x. Okay, that's the derivative of the first term times 2x. Then plus cosine of x squared times the derivative of 2x, which is 2. So at this point, well, let's plug in. Downstairs you get 6. Upstairs, well, you're going to get sine of 0 times 0 times 0, which is super 0-y, gone. Cosine of 0, 1 times 2 makes 2. 2 over 6, also known as 1 over 3. All right. So here are sort of two ideas melded together, L'Hopital and Fundamental Theorem of Calculus. So, oh, there's another question.
Why didn't you stop at the first L'Hopital? Pull out the 1/3 and have sine x over x.
You could have stopped. Yeah, so there was a question that says, hey, you know, there's this idea that says if you have sine of something, I'll call it u over u, and you take a limit as u goes to 0, that goes to 1. Well, that's what we have here. We have sine of x squared over x squared. And the answer is, you could have if you spotted it. And there's other things you could also have done. You could have stopped at the second one. You said, oh, wait a second. I could have canceled the x's. I could have stopped there. But I just love saying, you know, I just want to keep going until I'm first like, oh. And so that's probably why. Yeah, there's lots of times. So oftentimes you do want to look for simplifications. So yeah, good question. All right, for the function f of x equals log of x plus 3 over x to the fourth, determine the intervals for when the function is concave up and when it is concave down. So this is a question about concavity. So concavity questions come to second derivatives. So we're going to be looking at second derivatives. And in particular, there's a basic rule of thumbs. So if my second derivative is positive, my curve has this type of shape. We call that concave up. And on the other hand, if the second derivative is negative, it has this type of shape, which is concave down. All right. So concavity is really about the second derivative, positive or negative. So we want to take the second derivative. Now, looking at our function, right now, it looks a little bit complicated. Log of x plus 3 over x to the fourth. The absolute values are there just to say, look, we'll make sure that we don't take a log of a negative number. Now, one of the things we can do before we take derivatives is always ask ourselves the question, is this the right function to take the derivative of? By which we mean, is there a simpler way to write this function? Because sometimes you can take a function that's given and rewrite it to be easier to work with. And log has these beautiful properties. So in our case, if we take them in and say, you know, I have a division, I can turn that into a subtraction. That'll make it easier to work with. We can even go one step further, which is to say, I have this power, and powers come down. So now we have a very straightforward function to work with. So we start here. We take our first derivative, and that would be 1 over x plus 3 minus 4 over x. If you like, you can write this as x plus 3 to the minus 1 minus 4x to the minus 1. And the reason I say you might want to do that is for the second derivative, that makes it pretty simple. It becomes minus 1, x plus 3 to the minus 2, and then plus 4, x to the minus 2. Because here the minus 1 comes down, x to the minus 2. So there's the second derivative. Now what is it we're after? Well, we want to understand what's happening to this second derivative. In particular, we want to understand the signs. We're going to see the signs, and it's going to help open up our eyes when we see these signs. So to get there, we want to figure out a couple things. So we look for where concavity can change. So concavity can change at two locations. F double prime is undefined, or where F double prime is 0. So those are the places we all want to look for. So to help us understand things, well, the undefined, that's easy to spot because that's where our denominators are going to be 0. So we say x equals 0, x equals negative 3. We've got to keep our eye on that. But now we have to say, well, is there any place where I have the second derivative is 0? So to do that, let's put everything over a common denominator. So minus x squared plus 4 times x plus 3 squared over x squared times x plus 3 squared. So that's minus x squared plus 4, x squared plus 6x plus 9, or x squared times x plus 3 squared. Which, let's see, that would be 3x squared plus 24x plus, really? You know, wait a second, let's be smart. I'm not being smart. I hate it when I don't do that. Okay, well, we can keep going, or we can be smart. Which way do you want to? Choose your own adventure. Be smart or keep going with the computation. Be smart. Look what you have here. Now, you might say, okay, you have something. What's your point? Well, this, let me rewrite it in a slightly different way. That's 2 times x plus 3 squared minus x squared. And what is this? It's a difference of squares. A squared minus b squared. It's one of the things that you should look for. Why? Well, because a squared minus b squared is easy to factor. A minus b, a plus b. So in our case, we can say, well, look, this factors as 2 times x plus 3 minus x and 2 times x plus 3 plus x, which means it's going to factor in the numerator as 2x plus 6 minus x and 2x plus 6 plus x, or as x plus 6 and 3x plus 6. So that's what it's going to factor as. Now, that's what we would have gone if we kept going here, but it probably would have been a little bit not as clear because you would have gone 36, which is not terrible. Then you have to say, well, how does it factor? All right, so we now know how it factors. So it factors in the following way. So the numerator is x plus 6. And we also had a 3 times x plus 6, which we can factor a 3 out. So 3 times x plus 2 divided by x squared times x plus 3 squared. Which means, what do we care about? Well, we also care about negative 2, because that's where our second derivative is 0, and negative 6, because that would make the second derivative 0. So time to draw a line. The line must be drawn here. This far, no further. Put the points down, and the last thing to do is to say, we care about the second derivative between these numbers. So what we do is we start plugging in values. So we pick some values. Well, what's a number bigger than 0? A billion. Well, probably 1 is easier to work with. So plug it in, and you'll see you get positive, 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 positive. everything's positive, life is good. Second derivative is positive for above 0. How about between 0 and negative 2? Well, negative 1. So you get negative 1 plus 6 is positive, 3 is positive, negative 1 plus 2 is positive, and downstairs, because you square, you're always going to get a positive, so you're still positive. All right, between negative 3 and negative 2, well, negative 2.5. Positive, positive, but negative. See, because negative 2.5 plus 2 will be negative. Downstairs is positive, so that means we flip. There's a sign change. All right, between negative 3 and negative 6, let's say negative 4, positive, positive, and negative 4 still negative. So another sign change, still negative. And below negative 6, say negative 10, we get negative, positive, negative, which means positive. So, what's the answers? Well, this one, you can certainly say the following is true. When are we concave up? Well, from negative infinity up to negative 6, that's when we're concave up. And from negative 2 up to 0, and from 0 to infinity. Now, there's a small subtlety. You may say, well, why don't we say from negative 2 to infinity? The small subtlety is to say, well, our function is not defined at 0. So that's a problem. But that's okay. We wouldn't take any points off for the small subtlety. Concave down, negative 6 to negative 3, because that's where I'm negative, and negative 3 to negative 2. Again, we're careful because at negative 3 our function is not defined. But there you go. There's the answer. Okay. So if you see concavity, think second derivative. All right. The volume formed by spinning the region between y equals f of x and the x-axis for a less than or equal to x less than or equal to b is given by 2 pi times the integral from a to b of x times f of x. That's actually a fun fact, and something that the Calc 2 students were working on this morning. Determine the value of d greater than 0 so that the volume formed by spinning the region between y equals x to the d minus x to the 2d and the x-axis for 0 less than or equal to x less than or equal to 1 is maximal. Now here, there's a key word, maximal. We're trying to do a max. So what kind of problem are we doing? Well, this is optimization. So if you ever say, look, I'm looking for the largest or the smallest, the maximum or the minimum, that's optimization. So how do you do optimization problems? Well, it's pretty straightforward. The goal is find a function of one variable. Now sometimes you'll have several variables and you use constraints and you get down to 1. Okay, now you have that function, you take the derivative and look for your critical points. And that is mostly, that's like 95%, is finding that critical point. Because once you're there, the last piece is you interpret. In other words, you take that critical point and you use that to figure out, okay, was I looking for that location? Was I looking for a value? Now, occasionally, you may have to check. So it may include the instructions, verify that it's a max. Well, then you apply some sort of a test, a first derivative test or a second derivative test. So what do we have? Well, let's see what we have. We're told the formula. So our volume here, we follow the formula, is 2 pi integral from a to b of x times f of x. But here, our f of x is x to the d minus x to the 2 times d. And I guess we should have said a to b. We can replace a and b with 0 and 1. So that's the volume that we're going to get for any choice of d. So this is an interesting thing where we're doing an optimization problem which involves taking a derivative. But before we can take a derivative, first we have to take an integral. Now this is not one of those fundamental theorem of calculus like, oh, don't they cancel out? No, you got to do the work. You got to do the work. So what does the work tell us? Well, let's do the integral. To do this integral, what you would do is multiply the x through. So we're not going to do it yet. We're going to set ourselves up. So we oftentimes say, is there some simplification we can do to our integral to make it nicer? So look for algebra. So this is an algebra thing. distributing the x through. Now we integrate. All right. So the integral of the first term, well, you add 1 to the exponent, and then you divide by the new exponent. The integral of the second term, similar thing. Add 1 to the exponent, and then divide by the new exponent. And then we're going to evaluate from 0 to 1. And here we come to one of the most interesting problems I ever encountered. I didn't anticipate this mistake, but now you have to plug in 1. If I have 1 to the power d plus 2, what does 1 to the power d plus 2 become? It's 1. 1 to any power is 1. That was, we didn't anticipate people would have a struggle with that idea. But it turns out 1 to any power is 1, and 0 to any power is 0. Well, you might say, what about infinity? Don't worry about that. So, you plug in 1, you get 1 over d plus 2, 1 over 2d plus 2. Plug in 0, all the terms disappear. Okay, so that's what we're trying to optimize. Well, so now what? Maybe we can write this as d plus 2 to the minus 1 and 2d plus 2 to the minus 1. Now, that's our function of one variable. So we've done our first part. Take the derivative. So taking the derivative, we have the 2 pi in front. Then we're going to get minus 1, d plus 2 to the minus 2. And then minus minus makes plus, 2d plus 2 to the minus 2, and then times by 2, because I got to follow the chain rule, which means to multiply by the derivative on the inside. So there's our derivative. What are we looking for? We're looking for critical points. The kind of critical points we're almost always going to look for is where does our derivative equal 0. So we're going to set the derivative of volume equal to 0. So what's our derivative? Well, we'll clean up a little bit. 2 pi, we have minus 1 over d plus 2 squared, then plus 2 over 2 times d plus 2 squared. Now, when we set this equal to 0, obviously the 2 pi is not going to be 0. So that tells us that this part on the inside has got to be 0, which means that these two have to be equal in size. So in particular, we can conclude that 2 over 2d plus 2 quantity squared is the same as 1 over d plus 2 quantity squared. All right. So cross multiply to get rid of fractions. 2 times d plus 2 squared is 1 times 2 times d plus 2 squared. And we're pretty close. Just got to do a little bit of algebra, our favorite thing. So on the left-hand side, when we expand this out, that would be 2 times d squared. Then there's going to be a plus 4d times 2, which makes 8 times d, plus 4 times 2, which is 8. That's going to be equal to 4 times d squared plus 4d times 2, which is 8 times d, plus 4. Well, the 8d's cancel. Nice. Subtract the 2d squared and subtract the 4. You'll get 2 times d squared equals 4. D squared is 2, which tells us that d is the square root of 2. Now you might say, wait, how do you know it's the positive square root of 2 and not the negative square root of 2? See, for that, the secret is we read the problem. The problem tells us that d needs to be positive. Now, and it says, just find it. There it is. So we're done. We're done. Now, if we wanted to, we could apply a test, but it didn't ask us to apply a test. So we took the derivative, we got the critical point. In this case, our interpretation is the point that we found, that's what they're after. So we're good to go. All right. Maybe I need to pick up the pace a little bit here. Okay, well, we'll see. All right. Find the absolute maximum and minimum for g of x equals e to the x minus e times x, where I'm between 0 and 3. So this is an absolute maximum and minimum. Now, again, it's an optimization problem, but here there's another key word, absolute. Now, when you see the word absolute maximum and minimum, that tells you it's a very particular type of problem. And I like to call this sort of the Santa Claus problem. So how do you find absolute max and min? There's a procedure. And so what is it? Well, the first step is you make a list. Now, what does the list consist of? Well, the ends, where your derivative is 0, and where your derivative does not exist. Now, the second step is you're going to check it. And what do we mean by check? So plug in the points on your list to the function. And then the last step is we're going to find out which points are nice. Largest output is your max, and the smallest output is the min. So make a list, check it, see which ones are nice. So here we go. So let's make our list. Here's our list. Now, automatic free points 0 and 3. Cool. Next, we'll take the derivative. G prime of x is, the derivative of e to the x is e to the x, and the derivative of e times x is, does anyone know the derivative of e times x? D. Yeah. Because there's a constant times x. Even though, yes, e is a really special constant, it's still a constant, so you have to treat it like one. Now, in this case, there's no places where our derivative is undefined, but we can say, does this ever equal 0? In other words, is there a value for x where e to the x is equal to e? Well, e to the x is equal to e to the 1, so that tells us that x equals 1 is a potential point on our list. Now, why do I say potential? What do I have to check before I add it to the list? Suspiciously pointing at the interval here. I have to check if I'm in this interval. Now, is 1 between 0 and 3? Yes, it is. What if 1 wasn't between 0 and 3? It doesn't make the list. You only keep the points that are in the interval. So if I'd gone to point 5, no, forget it. You're out, 5. I don't like you anymore. No, it's okay. I like 5. It's perfectly fine. All right. So there's our list. So we've made the list. Now plug it in. So when we say plug it in, that means we're going to plug it into our original function. You'll notice one of the things that we didn't do is we're not checking to see if this point at 1 is a max or a min. No, it's not worth our time, because that's not how absolute max and mins work. When you're looking for absolute max and mins, you make a list and you plug them into the original function. Don't classify. Classification wastes time. All right, plug in 0. We'll get e to the 0 minus e times 0. Well, that's 1. Plug in 3. We're going to get e cubed minus 3 times e. Which, well, we'll think about that in a few minutes. And g of 1, e to the 1 minus e times 1, which is 0. Okay, well, we should think a little bit about e cubed minus 3 times e. What can we say? Well, that's e times e squared minus 3. Now, e squared, that's certainly not small. It's bigger than 4. So this is at least as big as e. So it's certainly going to be bigger than 1. So we've done the plug in the points. The last thing is we scan our list, the outputs. And we say, okay, which outputs are largest and smallest? Well, in this case, the largest output, that's e cubed minus 3e. So this is our absolute max. Smallest output, well, that's at 0. That's our absolute min. So we had one of our absolute max, that happened at an endpoint. Absolute min happened in the middle. You might have a case where the absolute max and the min occur at the two endpoints. You might have a case where both points are in the middle. It just depends. But just follow the process. Make a list. Plug them in. Largest is the max and the smallest is the min. Okay, good. This one might look familiar. We did this a little while ago. It's good to remember. Find the integral of sine theta over cosine squared theta plus 1 minus sine 2 theta over cosine squared theta plus 1. And make sure to indicate any substitutions that were used. So in this case here, this is a situation where it's oftentimes better to break integrals apart. Now, sometimes it's better to break integrals apart, and sometimes it's not. So don't always rush to break things apart. Why do you break things apart? Well, the answer is you break things apart if it makes things simpler. If you're like, well, on part of the integral I'm going to have this idea, but for another part of the integral I have a different idea. And if you have different ideas, it makes sense to pull it apart. On the other hand, sometimes when you break things apart, you're like, ooh, I actually need the pieces combined to get things to work nicely. So be careful, be careful. Now here, on the last part, there's sort of an incompatibility. You have a 2 theta and a theta. That's not good. We don't want that mixing up. So we're going to replace the sign of 2 theta with 2 sine theta cosine theta. That way, everything is a function of theta. It's more compatible. It's easier to follow. Now, when you're looking for substitutions, and there's probably an idea that we're going to look for substitutions, one of the clues is the fact that it says, talk about the substitutions you're going to use. So that's a pretty good clue that we should think about substitutions. So when you're looking for them, where do you look? And the answer is, when you're looking for substitutions, you look in 2 places. So if I have f of g of x, g prime of x dx, this is where I have the substitutions. You either look for a function on the inside, or you say, hey, I have something that's a nice derivative, that I recognize that this is a derivative. And if we're in that setting, then we know what to do. All right, well, what do you have? See, if I look at either one of these, the cosine squared theta plus 1, one thing we could try is, well, what if we set the inside as being this whole denominator? Maybe that's the idea. Well, we try it and see what happens. If u equals cosine squared theta plus 1, du will be 2 times cosine theta times minus sine theta d theta. We say, well, that's terrible. That's not at all what we need. But then our eyes say, ooh, wait a second. Bad choice for the first one, awesome choice for the second one. And we're happy. We say, okay, well, that's the right substitution in the second case. See, you try stuff. And if it doesn't work, okay, try something else. But maybe it works for a different part. Okay, so this substitution was the right substitution in our second integral. So if we make that substitution, you'll notice that there's a minus here. So if you bring this in as a plus and a minus, you'll see you have a du upstairs and a u downstairs. So this becomes the integral of du over u, which means that this will become log of u, which plus c, and then replace log cosine squared theta plus 1. All right, so that's the second one. All right, now let's come back here. So the whole thing didn't make sense. So now we say, is there maybe something simpler? Well, one idea is we say, okay, attempt 2. Try cosine. Maybe just that little piece. So if we try u equals cosine, we'll see du is negative sine. And now we're like, perfect. We have a sine theta d theta. You might say, but you don't have a negative. All right, now I do. And now you say, but wait, you've changed the problem. Aha, now I haven't. So you can modify things. When you only have constants to worry about, constants are easy to fix. Functions are not, but constants are. So if we make that substitution, we'll have minus the integral of du over u squared plus 1. Now this one is on our list of integrals. In fact, I would say this is one of the best looking integrals out there. Arctangent, of course, plus c, and then we make the substitution back. Arctangent of cosine theta. Okay, well, we see how we've got the two pieces, and then we just put the two together. Because we started by separating, we did them individually. Now the answer is put them back together. Minus arctangent of cosine theta plus log cosine squared theta plus 1 plus c. I only need one constant. So the two constants merged together. In some sense, constants are like sponge. Constants absorb other constants. So you only need one. Find the average value for the function f of y equals 2y plus 4 sine of y over the interval from 0 to pi. Now, there's nothing really tricky about this. We have to know a few things. First off, the type of problem says this is an average value problem. Now, average value is different than average rate of change. So make sure you get the right idea. So for average value, it's 1 over b minus a, integral from a to b of f of x dx. So it's not terribly far off from the average rate of change, but you want to make sure you get the right setting. Now, I say there's one subtlety, which is these are variables where you have the name of y. Does that change anything? And the answer is no. No, variable names aren't really sacred. We just choose some which are convenient, and we follow them for consistency's sake, and we've all sort of informally agreed we're going to use x as much as possible, not because x is somehow special, but just because it stopped reducing the number of arguments about what to use. So it's okay that it's y. So what do we have? So we're going from 1 over pi minus 0, integral 0 to pi of 2y plus 4 sine of y dy. So there's a 1 over pi in front, then just integrate piece by piece. The integral of 2y is y squared. Plus 4, the integral of sine. What's the integral of sine? Negative cosine. Yeah, sine and cosine are just, they're kind of trip you up a little bit. So be prepared. You know, make sure you remember what the right signs are from 0 to pi. So we have a 1 over pi, then plug in pi squared plus 4 times minus cosine of pi. All right, and parentheses around that. Subtract 0 squared plus 4 minus cosine 0. Okay, and I think one more. There we go. I think that's the right number of parentheses. Certainly there's a lot of parentheses here. All right. Well, zero is 0. What's cosine of pi? Negative 1. So minus minus 1 means that'll become a net plus 1. So we have 1 over pi squared plus 4. Cosine of 0, plus 1, minus minus. So you see there's a minus and a minus. Two wrongs become a right. So plus another 4. So in here, these combine, they don't cancel. And I should have been putting equal signs all the way down. And we have 1 over pi squared plus 8. Okay, good. Now on a side note, one of the things, you'll notice we didn't put plus c. Why? Because this is a definite integral. When it's a definite integral, you don't need the plus c, because the c's end up canceling. When it's an indefinite integral, you definitely want it. So pay attention. If it's a definite integral, get your, don't need the plus c. If it's not, make sure it's there. Because what do we want? We want all the points. That's the goal. Got to catch them all. All right. Let f of x equal the integral from x to x squared minus 2 of the square root of 5 plus 11t squared dt. Determine the tangent lines at the points where y equals f of x crosses the x-axis. Now, this one sort of makes it go, what? All right. You might even be tempted to say, there's a big curve. I can skip it. But no, we're not going to yield to that temptation. We're going to solve the problem. So we start thinking about what's happening here. So it says where y equals f of x, we cross the x-axis. Now, to cross the x-axis really says y equals 0. Okay, so we're looking for the tangent lines where we have y equals 0. So that's good. That's a piece of information. So now we start looking at this function. We say this is a strange function. We have this curve, square root of 5 plus 11t squared. I don't know exactly. It does something like that. And then we integrate between two values. It just depends. Maybe here's x squared minus 2, here's x. And it's this area between those two. So now we say, okay, how can we possibly get a 0 out of this integral? Well, we're definitely not going to get 0 in a case like this, where these things are far apart, because we're going to have area. So how can we get 0? Well, any suggestions? And what? Well, now one thing we shouldn't try to do, by the way, is try to find that integral. It's a very challenging integral. Even the Calc 2 people are like, oh, I don't want to do that one. Okay, for good reasons. The key here is to look at the ends. So here's a case when you have 0, is if x and x squared minus 2 were exactly the same. Because if x and x squared minus 2 are exactly the same, how much area is there? The answer is there's no area. So the key here is that we're going to cross the x-axis. That'll happen when x is equal to x squared minus 2. Or when 0 equals x squared minus x minus 2. And we cross our fingers to hope that, please let our belief that everything factors continue. Does x squared minus x minus 2 factor? It does, as x minus 2 and x plus 1. Okay, so what does that tell us? Well, that tells us that the following is true. F of x will equal 0 when x equals 2 and x equals negative 1. So this is, we're looking for these tangent lines. That's where we're after. Okay, so now we know which tangent lines we want. So given that we know which tangent lines we want, the next thing for us to say is, okay, we know the points. In fact, not only do we know the x coordinates, we even know the y coordinates, because that's at 2, 0 and negative 1, 0. Remember, we said y is 0. So we have the points of our tangent lines. What are we missing to get our tangent lines? The slopes. So now we're going to switch gears. Say, okay, we need to find our derivatives. So we need f prime of x. So f prime of x, that's the derivative of the integral from x to x squared minus 2, square root of 5 plus 11t squared dt. And now we're like, this looks fun, as in fundamental. This is the fundamental theorem of calculus coming back. So what does the fundamental theorem of calculus say? Well, there's sort of 3 layers. The very simple layer is if I go from some constant to a function, I'll call it h of x. Some constant just to x. Sorry, I was thinking of layer 2. Some constant to x of f of t dt, that's f of x. So that's the one we started with. The next layer says, hey, why don't you put a function upstairs, h of x? Now what is this? Well, this is a function inside a function. So it's this function h of x inside of this cumulative total function. So you do the chain rule, and you get f of h of x times h prime of x. The last layer says, what if I go from a function downstairs to a function upstairs? And for that, you do the following. F of the upstairs function times the derivative of the upstairs function, subtract f of the downstairs function times the derivative of the downstairs function. So that's the fundamental theorem of calculus in the various stages of specificity. So, in our case, we're going to have the square root 5 plus 11, plug the top piece in, so that's x squared minus 2 squared, times the derivative of the top, which is 2x, minus the square root 5 plus 11, plug in the bottom, which is x squared, times the derivative of x, which is 1. So there's their derivative of our function. That's f prime. Now what do we need? Well, we need to plug in two values. F prime of 2, well, so we plug in 2. So 2 squared minus 2, that's 4 minus 2, which is 2. I'm going to square that. So that'll become 4 times 11, 44, plus 5. So square root of 49 times 2 times 2, which is 4, minus x is 2, so 2 squared again. 11 times 4, it's 44 plus 5 is 49. Square root of 49 times 1. Well, that's 7 times 4 minus 7, or 28 minus 7, or 21. Plug in negative 1. So if we plug in negative 1, we're going to get negative 1 squared, which is 1. Subtract 2 is minus 1. Square that. So that'll become plus 1 times 11. So we're up to 11. Plus 5 makes it 16. So square root of 16 times negative 2, which is 2 times negative 1, minus negative 1 squared times 11 plus 5 will be square root of 16 again, times 1. Or 4 times negative 2 minus 4, negative 8 minus 4, which is negative 12. So those are our slopes, 21 and negative 12. So now we just take our points and our slopes. So our two tangent lines are y minus our y coordinate, which is 0, is equal to our slope. I'll do this 2 first, so 21 times x minus 2. And y minus, again, 0 is equal to our slope, negative 12, times x minus negative 1. X minus minus makes x plus 1. And there's the answer. So that's fun. That's a fun one. We like fun problems. Now you might be getting a little bit nervous about some of these fun problems. I just want to say, we try to make the review problems maybe slightly more fun than the exam problems. I don't want you to be like, oh my gosh, if these are the review problems, what are the exam problems like? No, we want to, we work you hard in the exam review so that when you hit the exam, it's like, at least we didn't have those. So don't get too nervous. Don't get too nervous. Okay, let h of x be the function e to the 2x plus a e to the x plus b times x, where a and b are some constants to be determined. We don't know what they are yet. Given that the function is decreasing only between 2 and 5, determine a and b. Now, decreasing is code for saying that your derivative is negative. Now, okay, so what does that tell us? We now know that the function is negative only between 2 and 5. In fact, we can say less than or equal to 0. So in particular, that tells us that 2 and 5, that has to be places where our sign has to change, because I'm no longer going to be negative outside of those. So I need to have the derivative equal to 0 at x equals 2 and 5. So that's our way we can read that first part. Well, that's useful, because we say, okay, what is the derivative? H prime of x. So we take our derivative, that's 2 e to the 2x plus a e to the x plus b. And we have that we want the derivative to equal 0 at 2 and 5. So h prime of 2, that's 2 e to the 4 plus a e squared plus b, that has to equal 0. And h prime of 5, that's 2 e to the 10th plus a e to the 5th plus b equals 0. Now, two equations, two unknowns. What do? The best thing to do is to combine them. In other words, knock out a variable. So here's something we can do. Let's take this first equation and subtract it from the second. So if we do that, why is that useful? Well, certainly 0 subtract 0 is 0. But the reason it's useful is I take b, subtract b, the b's vanish. Then I have a times e to the fifth minus a e squared. So that becomes a e to the fifth minus e squared. And then I'll have 2 e to the 10th minus e to the 4th. And now we say, ha, that is one variable. That's a solve. So what can we say? Well, at this point, we can move stuff around. So we can say that a times e to the fifth minus e squared is equal to negative 2 e to the 10th minus e to the 4th. Or a is equal to negative 2 e to the 10th minus e to the 4th over e to the 5th minus e squared. Did I make a mistake, or are we good? I think we're okay. So that's actually correct. Now you might say, wouldn't it be nice if we could simplify that? Can we? Said in a way that indicates we can. It turns out that you can simplify because e to the 10th is the same as e to the 5th squared. And e to the 4th is e squared squared. Now the reason I point this out is I have e to the 5th downstairs and e squared downstairs. So lo and behold, it's the difference of squares upstairs. Anyway, it's e to the 5th minus e squared times e to the 5th plus e squared divided by e to the 5th minus e squared, and those cancel. So that's a. A is negative 2 times e to the 5th plus e squared. Now that's only half of it. We also have to solve for b. So how do you solve for b? Well, the answer is you just you pick one. Doesn't matter which one. And you plug it in. So we get 0 is equal to 2 e to the 4th, picking the first one, plus minus 2 times e to the 5th plus e squared times, so that's my a, times e squared plus b equals 0. All right, well, can we simplify? We can. Well, at least we can see if anything groups. 2 e to the 4th minus 2 times e to the 5th times e squared. So that's minus 2 e to the 7th. Then I have minus 2 times e squared is minus 2 e to the 4th. So those cancel. There's still a plus b. And so that allows us to conclude that b is 2 e to the 7th. So now we know a, and we know b. So that's the answer to the first part, determine a and b. Now, answer to the second part. So, given the answer to part A, find the point of inflection. So if we're looking for the point of inflection, where do you look? Which derivative? Second derivative. And so we take our second derivative, and for simplicity, I'll still keep the A terminology here. So that's 4e to the 2x plus a e to the x. The b goes away. And we want that to equal 0. All right. Well, what does that say? You can factor out e to the x. That says 4e to the x plus a better be equals to 0. Now at this point we say, all right, e to the x is never 0. It's one of the nice things about the exponential functions. It's never 0. So that says that this part has to be 0. So we can conclude that we need e to the x to be negative a over 4. Now we pull out our a card. Here's our a card. So e to the x is negative times negative 2. So that makes positive 2 over 4, or 1/2 e to the 5th plus e squared. And finally, we say that's e to the x, take the log. So x is log of 1/2 e to the 5th plus e squared. And there's the answer to the second part. Oh, good. Whew, that one was fun. Okay. Find the area above the x-axis and below the curve y equals 2x minus x squared times e to the power x cubed minus 3x squared. So we have to figure a few things out. So this is an area problem. So in particular, we're told an area really between two things. Now, when you're doing an area between two things, you sort of say, okay, maybe you have your f of x up here, and you have your g of x down here, and you have your a and your b. So the basic formula for area is the integral from a to b, top minus bottom. So that's our formula that we're keying off of when we're talking about area. That's our area formula. It's the integral of the difference. Now, in our case, what do we have? Well, we have the x-axis as one of our curves. So that's an easy curve. This is the curve y equals 0. And then we have this other curve, y equals 2x minus x squared, e to the x cubed minus 3x squared. That one's maybe not so obvious what it looks like, and it's kind of a strange function. However, let's think about what we need. We weren't told where a and b are. So we have to figure out where that is. So we need to be above the x-axis and below the curve. So when you're not given your bounds, what you're looking at is you're looking for intersection. So we weren't told our bounds, so we got to find intersections. So let's think about this. Another way to write this expression is you factor out an x, 2 minus x, then you have e to the power x cubed minus 3x squared. And we say, when does this hit the axis? Well, it'll hit the axis when x is 0, and it'll hit the axis when x is 2, and then I have this other piece. Can I ever have the exponential function equal 0? No. Which says, okay, these right here, 0 and 2, are my bounds. And you can check, if I go between 0 and 2, I'll have a positive, positive, and a positive. But if, say, I'm below 0, negative 1, I'll have a negative number and 2 positives. Or if I'm above 2, I'll have a negative number and the 2 minus x and 2 positives. So it really is 0 and 2 are the bounds. So we now have our basic setup. It's the integral from 0 to 2 of our top function, 2x minus x squared, e to the x cubed minus 3x squared, subtract our bottom function, 0. Now in our case, subtracting 0 is pretty easy, so we don't need to worry about that. Now we come to how do we handle this integral? The integral of 2x minus x squared, e to the power x cubed minus 3x squared. Well, unfortunately, this function didn't make our list of integrals to know, which means we have to do something. There's got to be something for us to make progress on this problem. Well, going through our list of sort of things to test, we look and say, all right, well, there's no real easy algebra here. There's no trig identities. So the next thing to look for is substitution. And when you're looking for substitution, if you have a function and a function, that's a good place to start. So what if we tried this for u? So u equals x cubed minus 3x squared. Let's follow and see where that takes us. Du, what would that be? Well, 3x squared minus 6x. And then there's a dx on the end. Now, we don't have 3x squared minus 6x, but we have 2x minus x squared. These are really close, like really close to each other. And what do we mean by they're really close? Well, they differ by a factor. If you pull out negative 3, you'll see this becomes 2x minus x squared dx. We say, aha, success. Or if you were Klingon, kapla, which means success in Klingon. So there is that du sitting right there. All right, so that's great. So we're going to make that substitution, and let's see where it takes us. So the 2x minus x squared, well, let's move this minus 3 across. So minus 1/3 du, we'll say, is 2x minus x squared dx. So we get a minus 1/3 du. Then we have e to the u. That's great. But now, update the bounds. These were x bounds. We've got to update them to u bounds. So when you plug in x equals 0, 0 minus 0, well, that's 0. Plug in x equals 2. 8 minus 12. 8 minus 12, negative 4. Now, the bounds are kind of weird. 0 to negative 4. We usually don't like to have the bounds in that order. We like to have the smaller number on the bottom, bigger number on the top. Well, we can fix that. We just flip it. But if you flip the bounds, remember you have to change the sign. Well, that's great news for us because we had that negative in the front we didn't like. So 1/3 negative 4 to 0 of e to the u du. And now that we're at this point, the beautiful thing is I never have to go back. I don't have to remember that integral with respect to x anymore. I'm now totally focused on this integral with respect to u, never looking back. So this becomes 1/3 e to the u. Evaluate that from from negative 4 up to 0. So that's 1/3. E to the 0 is 1. Subtract e to negative 4. And there's the answer. That's it. Good. Good. All right, we are given the following. The line y equals 5 minus 2x is tangent to y equals f of x at x equals 1. The line y equals 3x minus 4 is tangent to y equals g of x at x equals 2. And the point 2, 1 is on this curve. F of y squared plus g of x squared is 4xy plus d, where d is something to be determined. Well, part 1, what is your d? And part 2, find the tangent line to the curve at the point 2, 1. So let's think about what we have here. So there's sort of two ideas being put together here. So we like this kind of problem, where we have multiple ideas coming together. What are the ideas? Well, we're given tangent lines, and tangent lines are storing information. So can we understand the geometric meaning of the information that's been given to us? So let's go through the two lines. So if y equals 5 minus 2x is tangent to y equals f of x at x equals 1. Now the way to interpret this says that this tangent line matches f of x at the value of the function and the value of the derivative. So if I want to know what f of 1 is, I say, well, what's the value of 1 on the tangent line? So it would be 5 minus 2, which is 3. If I want to know what the derivative at 1 is, I say, well, what's the derivative of the tangent line? Or if you like, what's the coefficient of x? In that case, it's negative 2. So the tangent line is storing the information about what's the value of the function and what's the value of the derivative. So that's the first line. Now the second line, that's going to come from the other part. So we have the line y equals 3x minus 4, which is tangent to g of x at 2. So g of 2, we plug 2 into this. 6 minus 4 is 2. G prime of 2, well, we take the derivative, or read off the coefficient, we get 3. So now we have our information. What is f of 1, f prime of 1, g of 2, g prime of 2? That's what was given to us, masqueraded as tangent lines. We also know that the point 2, 1 is on this curve. So what can we do? Well, we plug in x equals 2 and y equals 1. So if we do that, we get f of 1 squared plus g of 2 squared is 4 times 2 times 1 plus d. So I'm just literally plugging in 2 and 1 into my equation. And now we say, okay, we have information. See, f of 1 is 3, and g of 2 is 2. So I'm going to get 9 plus 4 is 8 plus the d. So solving for the variable d, we'll get 13 minus 8, which is 5. So that's the first part. We've solved for d. Now, the second part says find the tangent line. See, what do we have here? We have this function, and this is a very particular type of question we're looking at. In particular, I can place the 5. This is what we would call an implicitly defined curve. Now, what does that mean? Well, it means I don't have y as a function of x right now, or x as a function of y. I have x's and y's coming together in some beautiful cacophony of mathematics. So I don't know what y is as a function of x, but I somehow need to find the derivative of y with respect to x. So whenever you have an implicitly defined curve or some relationship, what's the key? So the idea is you think of y as a function of x. That's our key. And now take the derivative with respect to x. So that's the two ideas. If you have an implicitly defined curve, think of it as like, well, there is some relationship that exists out there. I just unfortunately don't have it, but I'm going to pretend like I did. And now I'm going to take the derivative, and anytime I come across the point where I say I have to take a derivative of y, I'll remember to use the chain rule. So here we go. We're going to take the derivative now with respect to x. So if we do that, we get chain rule 2 times the root of the inside, which is f of y, 2 f of y to the 1 times the root of the inside. Well, the root of inside is f prime of y, and then times the root of that inside. Yeah, we got to keep going. This is an onion problem. It has layers. It's also an onion problem in that we might cry a little bit by the end. But, all right, times the root of the inside. So remember, we're taking the derivative with respect to x, but we're thinking of y as a function of x. So I say, I got to take the derivative of y with respect to x. I'll call that y prime. Or if you prefer dy dx, whichever notation you like. So the next part, derivative of g of x squared. 2 times g of x to the first power. Now I take the derivative of the inside, that's g prime of x, and then I say, well, okay, do I have to keep going? Well, in a sense, yes, but now you're taking the derivative of x. That's our next inside part, and the derivative of x with respect to x is 1. So oftentimes we don't write that down. Okay, so that's the derivative of the left-hand side. Take the derivative of the right-hand side. Product rule. Derivative of 4x is 4 times y plus 4x times the derivative of y, and the derivative of y we write as y prime. And then 5 is a constant, so we don't need to take that derivative. Oh, done. All right. We're not done yet. The next thing that has to happen is we really need that y prime. We need that slope. So after we've done this, we're going to plug in x equals 2, y equals 1. That's our point. So we're going to get 2 times whatever f of 1 is, times f prime of 1, times y prime, which we're looking for, plus 2 times g of 2, times g prime of 2, is equal to 4 times 1, which is 4, plus 8 times y prime. So we plugged in x equals 2, y equals 1, carried that all the way through, and now we're going to use our information. We know that f of 1 is 3, because we found that earlier. We know that f prime of 1 is negative 2. We know that g of 2 is 2, and g prime of 2 is 3. So what are we up to? We have 2 times 3 times negative 2, which is minus 12 y prime. 2 times 2 times 3 plus 12 is equal to 4 plus 8 y prime. So we'll move things around. Move that minus 12y prime across. Move the 4 across. We'll get 8 is equal to 20 y prime, or y prime is equal to 8 over 20. Now, here we can simplify a little bit. Everything's divisible by 4, so that becomes the same as 2 over 5. Well, what is that? What you found is you found your slope. So this is the slope of your tangent line. You see, we probably should have made sure we knew what we were looking for before we started looking. But when we're looking for a tangent line, we need the slope. We already had the point, so that's why we were after that dy dx. dy dx gives us our slope. But now that we have our slope, we can just write our answer down. No more work required. Y minus our y coordinate, which is 1, is equal to our slope, 2/5, x minus our x coordinate, which is 2. And that's our line. And we're done. We can leave it like that. We don't have to simplify any further. All right. You and a friend are holding on two ends of a bungee cord. If you're not familiar with bungee cords, they're very stretchable. So for instance, if you're going to go bungee jumping, it allows you to stretch. But then it'll pull you back up. Hopefully before you hit the bottom, if it's done right. You start heading north and your friend heads east. It's surprising how many people do stuff and walking around with compasses. You know, it's like, you head north and I'm going to head east. All right, so let's draw a picture. So we start off and we're heading north. All right, so here, this is us, and your friend is heading east. Okay. And there's your friend heading east. All right. A few seconds later, you have gone 10 feet and are moving at 3 feet per second. So let's see, we should make some notes here. So we're the ones going north. So this is 10 feet. And here, 3 feet per second, well, that is talking about how fast we're changing. Your friend has gone 24 feet. Oh, they're faster than us. And they're moving at 7 feet per second. Ooh, all right, they're really booking it. Now, at that moment, what do we want? We want to determine the length of the bungee cord. Yeah, we forgot to draw that. Let's draw that in. So there's this part, this bungee cord stretched between us. So it's getting pulled, and we want to say, what's that length? How long is it? And how fast is that changing? Okay. So let's think about what kind of problem this is. What kind of problem is it? Do you recognize it? It's related rates. Yeah. So how do we know it's related rates? What are some things that give it away? Well, basically, we kept seeing rates showing up. 3 feet per second, 7 feet per second. Find the rate. It kept giving us lots of rates. And there were multiple rates given. So there was more than one rate. See, it's not related rate, it's related rates. So when you have several rates involved, that's almost always a related rates problem. Now, someone mentioned triangle. Yeah, you'll notice a lot of things happen with right triangles. So in particular, for related rates problems, you tend to look for things like the Pythagorean theorem. Very common. It's a great theorem. And what else do you look for? Well, you look for similar triangles. That gets used a lot in related rates. You also look for geometry. And when I talk about geometry, I mean things like areas, volumes, those types of things. Like the volume of a sphere, or you have a melting snowball, or you have a cake that's formed in a cylinder, and you want to know how fast is it growing so you know how much frosting you need. Things like that. And occasionally, they just give it to you. They're just like, here's a formula. Oh, really? Come on, that takes all the fun out of it. Most of the time, it won't be here's a formula type problem. But you have to figure it out. Now, in our case, we can see that it's set up because we're heading in a nice perpendicular directions. So it's set up to be a Pythagorean theorem type problem. All right, so what do we need to do? What's our next step? Well, we've identified what the problem is, and usually the next thing is to draw a picture, but what else do we need to do? Find derivatives? Right, find an equation. Yes, we need to find an equation. Now, before you can find an equation, you have to get variables in the picture. And so, one of the things you have to decide is what is varying. See that word variables? It has like that vary part in it. So what's changing? Anything that's changing, put in a variable name. All right. Now, you might say, well, which names do we pick? Well, try to not be creative. X, Y, and Z are fantastic because they're not creative. You don't want to be like, I don't even know a name that starts with X. Okay, or, Sally and Bob and Jenny, No, X, Y, Z. Easy. Pick easy names. All right, we see that there are three sides of the triangle. All three sides are varying. Each side gets a name. What's the equation that relates these three together? Pythagorean theorem, which says x squared plus y squared equals z squared. Okay, so we're working through our related rates process. What do? We draw a picture, we label variables, we set up equations. Now, I will say in the past, sometimes you might have multiple equations. And this has happened where you're like, we have, if you remember, there was a problem about frosting a cake. Well, you had to set up one equation for surface area and one equation for volume and work things out. So it might just be one equation, might be several. Don't panic. Just figure out what are the right equations, our right equation. And now, the important part. Take derivative. And there's a subtlety here. We just talked about implicit differentiation. Now, implicit differentiation and related rates sometimes are a little bit murky, but because you're like, oh, you're doing the same thing, but it's slightly different. So in the implicit differentiation, the one we did in the previous problem, we said think of everything as depending on x and take the derivative with respect to x. But x was showing up. X was one of our variables that was in our equation. When we're doing related rates, we're going to think of everything as t. There's not even a t to be seen. So everything depends on some unseen variable that's out there in the ether. So we're going to take the derivative with respect to t. What do you get? Well, just go crazy with your chain rules. 2 times x to the 1 times the derivative of x with respect to t, dx dt. Then go to your next one, derivative of y squared. 2 y to the 1 times the derivative of y with respect to t equals 2 times z to the 1 times the derivative of z with respect to t. So here we took the derivative of everything with respect to t. Because all these things are varying, and everything which is varying depends on your t. Now we don't know what x, y, and z are. It's very tempting to say, oh, wait a second, don't we just sort of throw in these numbers here, this 10 and 3, this 24 and 7, to get equations for x and y? But no, what you're being told is like a snapshot. What happens at that moment? You don't know what happens slightly before that moment or slightly after that moment. You just know what happens at that moment. So, where do you go from here? What's our next step? Well, right. We plug in what you know and solve for what you don't. Now, what do we know? Well, we know x and we know dx dt. Similarly, we know y and we know dy dt. So, we have two equations and there's two things we want to find. So let's start with the first equation. We have 10 squared plus 24 squared is equal to z squared. Well, that looks a little bit challenging, but the good news is this is not quite as bad as it looks, because this is really 2 times 5 squared plus 2 times 12 squared. Now you might say, why are you doing that? I'm essentially saying that 10 and 24, they have a factor of 2 in common. So if you take advantage of that, you really can say, think of it as 2 squared times 5 squared plus 12 squared. Now, if you hang out with right triangles a lot, and of course we all do at some point in our life, 5 and 12 show up pretty frequently. Well, 5 squared is 25, 12 squared is 144. If you put those two together, 25 plus 144, what do you get? 169. Now, is 169 a nice square number? Turns out it is. So that is 13 squared. So, lo and behold, this turns out to be 26 squared. So z squared is 26 squared, which tells us that z is 26. So that's how long the chord is between the two of us. And it seems like the friend has done most of the work. They've moved 24 feet, and the chord is only 26. We need to work harder. Okay. Well, now that's just from the first equation. From the second equation, well, let's go ahead and cancel the 2's before we even start. And let's see, do we have space? Maybe we have space over here. So we have x times x prime. So that's 10 times 3. Then we're going to have y times y prime. So that's plus 24 times 7. Ooh, that's going to be an interesting number to compute. And that's going to equal z times z prime. 26 dz dt. Well, 10 times 3, that's not bad. That's 30. 24 times 7, yep, that's the number. It's 168. But in fact, looking at this, we can save ourselves a little bit of work and say all these things have a factor of 2 in them. So if you divide everything by 2, then instead of 10 times 3, you can do 5 times 3, which is 15. And instead of 24 times 7, you have 12 times 7, which is 84. And that equals 13 times dz dt. 15 plus 84 becomes 99. Divided by 13, and you get your dz dt. So, dz dt is equal to 99/13 feet per second. Okay, so that's the length of the chord and how fast it's changing in between. So related rates problems are fun. Just don't panic. Think about the setup. Figure out what's the right equations. Label things as you need. Draw pictures. Think about them. And make sure you take the derivatives. Everything that's varying needs a variable. All right. Find the value of a greater than 0 so that the average value of f of x equals 30x minus 4x cubed on the interval from 0 to a is maximal. All right, well this is going to be fun because this is going to tie a couple of ideas together. We're looking for average value, so that's another average value problem. And we're doing optimization because we see the word maximal. So, good times. So, here we go. So the average value from 0 to a is 1 over a minus 0, integral from 0 up to a of the function 30x minus 4x cubed. All right, so there's our function we're trying to optimize. But we should clean that up. So that becomes 1 over a of the integral from 0, oops, no, we can integrate. Integral of 30x, you know that one? 30x? 15x squared. Integral of 4x cubed, x to the fourth. And we're going to evaluate from 0 to a. So we have the 1 over a in the front. 15a squared minus a to the fourth. And then when you plug in 0, you get 0. So this becomes 15 times a minus a cubed. So the average value from 0 to a is this expression, 15a minus a cubed. Now we're trying to maximize this. So here, this is what we're trying to maximize, this expression. Well, the good news is it's a function of a single variable. It's a function just of a. And we like functions of one variable. So now that you have a function of one variable, what do? You take a derivative. So 15 minus 3a squared. And we set that to 0 because we're after our critical points. So that becomes 3a squared is equal to 15. A squared is equal to 5. So a is plus or minus the square root of 5. But we want the plus. Now how do we know we want the plus? Because it told us that a should be positive. And so that's the answer. A is the square root of 5. So if we go from 0 to the square root of 5, this function, 30x minus 4x cubed, has the largest average value. So that's kind of unexpected. You wouldn't have thought square root of 5 when you started this problem. But you follow the work. You do the work. And it comes out rather nicely. I think this is a problem that's on the first quiz in Calc 2. So, good times. Something to look forward to next semester. All right. Suppose that the weight of a cloud in tons after t hours, denoted W of t, decreases proportionally to its surface area and that this process speeds up over time until the cloud is completely gone. We can approximate this behavior with the differential equation. W prime equals negative 5/3 times t times w to the 2/3, w to the 2/3. Given that the cloud initially weighs 1,000 tons, how many hours until the cloud is completely gone? Now looking at this, we try to think, okay, what kind of problem is this? Well, there's a clue here. It tells us it's a differential equation problem. So that's a good idea that we're probably going to do a differential equation to solve this. But even if we didn't say the differential equation, when you see this expression, where there's a w prime and a w in the same equation, this is a differential equation problem signal. So we know it's a differential equation problem before we even start. So that's good to know where we're going. In fact, most of this we can ignore, like 95% of the statement. We need the following two facts. We need to know the equation w prime is negative 5/3 times t, w to the 2/3, and this part initially weighs 1,000 tons. So that's going to tell us initial means 0 and 1,000. Now, how do we know it's 1,000 is right? Because the weight is in terms of tons. So we do want that number, 1,000 for tons. All right. So this is a separable differential equation, which is the only kind of differential equation that you have to worry about. So we go through the process. Another way to think of w prime, dw over dt. So first step is separate. dw divided by w to the 2/3 is equal to negative 5/3 t dt. Or you can write this as w to the minus 2/3 dw. Oftentimes you'll see that when it comes to integration, it's easier to have exponents upstairs. So like w to the negative 2/3 instead of 1 over w to the 2/3. Similarly, like square root of w becomes w to the 1/2. So what's our next step? We've done our separation. Our next step is integration. So we're going to integrate both sides. So we integrate both sides. W to the minus 2/3 dw. That's going to be equal to the integral minus 5/3 t dt. Well, you add 1 to the exponent. So you're going to get w to the positive 1/3. And then you divide by the reciprocal, which means you really multiply by 3. That's going to be equal to negative 5/6 t squared. Because in this case, t to the 1 becomes t squared divided by 2 plus c. Now, we've integrated. Our last step is to figure out what c is. So this is the uncomplicate stage. So to figure out c, we can actually start right here. We don't have to rearrange. We can, as soon as we've gone to this point, we can figure out c. Now, sometimes it's nice to rearrange. Sometimes it's good to wait. Wait a second. I just said to do the same thing twice. Sometimes it's good to do it right away. Sometimes it's good to wait. It's okay. Just whatever is convenient. I always like to look and say, does it look like it's going to be simple to work with? And if the answer is yes, I say, let me take care of it now. If the answer is no, I say, I'll wait and worry about it later. So we're going to plug in here. That's our t. T equals 0. And we're going to plug in w as 1,000. So we get 3 times 1,000 to the 1/3 is equal to negative 5/6 times 0 squared plus c. Well, the good news is 0 is really easy to work with. The other good news is that 1,000 is not just a random number. 1,000 is 10 times 10 times 10. So it's 10 cubed. So this becomes 30. So we now know that c equals 30. So we have now, updating, 3w to the 1/3 is equal to minus 5/6 t squared plus 30. And at this point you might say, aha, now you solve for w. And the answer is no. I mean, I guess the answer is you could, but what are we after? See, it didn't ask us to find w. It asked us to find something. So let's understand what it's asked. It's asking for how many hours until the cloud is completely gone. So how many hours means we need to find a t. So we're not solving for w, we're really going to solve for t. So the question is, which t? So we say, okay, if the cloud is gone, what does that mean? Well, to be gone, and really to be gone completely, says I really need to say there's no more cloud, which means there's no cloud left, w equals 0. So what we do is we come into here, we're going to put w equals to 0, and once we have w equal to 0, we're going to solve for t. So 3 times 0 to the 1/3 is equal to negative 5/6 t squared plus 30. Well, that's gone because that's 0. 5/6 t squared is equal to 30. And then we're going to divide by 5 and multiply by 6. We end up with t squared equals 36. And then we say, aha, that's t equals 6. And you might say, well, plus or minus? It's plus, because the cloud is shrinking. So we want it to move forward in time. And if we wanted to, we can even say t equals 6 hours. Now, they didn't say that we had to include units, but if they did, we would, because t is an hour measurement, and so we get 6 hours. Now, that's it. That was the last one. So that was 17 problems, and we haven't even taken 2 hours yet. And you only have to do 7. So that means you have plenty of time. Don't rush. Think about what's being asked. Because oftentimes, people try to read too fast and be like, okay, let me start before I understand what the question asks. Don't do that. Take your time. Think about these things. Practice, and you should be okay. So, good luck.